This video is for ELEC 1510 Logic Design. This is Lecture 14, Part 1 on the SR latch, corresponding to textbook section 5.3. In sequential circuits, we use storage elements that actually have a memory component to them. This means that these elements, unlike anything that we've used in combinational circuits, can remember their previous states. There are two main types of storage elements. Latches, which are controlled by signal levels. These are called level-sensitive devices. And flip-flops, which are controlled by clock transitions, and we call these edge-sensitive devices. The SR latch, as a circuit diagram, looks like this. It's comprised of two NOR gates, here and here. The input to the first NOR gate is S, which stands for the set input, and the output of the second NOR gate here, meaning that there's feedback. So we can say that the output of that NOR gate, Q prime, is equal to S or Q prime. The output of the second NAND gate, Q, is equal to R, which is called the reset line, or the output of the first NOR gate, Q prime, parentheses prime. Q is just called the output of the latch. Q prime is the complemented output of the latch. Let's analyze the behavior of an SR latch for all possible values of S and R using a truth table. I've rewritten the expressions for Q and Q prime on the diagram to the left. Let's actually analyze the second case in the truth table first, when S is a 0 and R is a 1. This means that set is 0 and reset is 1. Well, in the second expression for Q, R is a 1, so we get 1 or Q prime, which is equal to 1 prime, which is equal to 0. So Q here is a 0. In the top expression, S is a 0, and Q, as we have already determined, is a 0. So we get 0 or 0 prime, which is 1. Let's now analyze the second line in the truth table. Set is a 1, so in the top expression, we get 1 or Q, parentheses prime, which is equal to 1 prime, which is equal to 0. So Q prime is 0. In the second expression, reset was a 0, so we get 0, and then Q prime, as we already determined, was a 0. So we get 0 or 0 prime, which is 1. Q is a 1. Those are the two most simple cases. Now let's analyze the case when both S and R are 0. I'll start with the top expression. S being 0 means that we get 0 or Q, parentheses prime, so we just get Q prime. We can't say that there's any definitive value. Let's move on to the second expression and see if we can clear things up. Reset being 0 means that we get 0 or Q prime, so we just get Q out. So there's nothing more that we can say other than Q is equal to Q and Q prime is equal to Q prime. For all of these expressions, Q and Q prime are actually opposites, and so we'll call these stable states. Now, in the very last line in the truth table, S and R are both 1. So in the top expression, we get 1 or Q, parentheses prime, which is equal to 1 prime, which is equal to 0. For the bottom line in the truth table, R is 1, so we get 1 or Q prime prime, which is 1 prime, which is also 0. Since Q and Q prime didn't turn out to be opposites in this case, we call this an unstable state. This is actually an illegal set of inputs that we don't want to occur. The output of the latch will be unstable. It'll actually oscillate between 0 and 1 for both Q and Q prime, and we don't ever use that set of inputs. The only thing that's slightly mysterious here that we've never seen before is the output being equal to itself. We actually call this the no change scenario. That means that Q and Q prime stay the same, and they could have previously been 0 and 1 or 1 and 0. They actually remember what their previous state is when S and R are both held at 0. So this means that they have some memory. An alternate construction of an SR latch is shown here. This one uses NAND gates rather than NOR gates, but has the same feedback paths. The difference here is that when set and reset are both held at 0, we produce an unstable state. Set and reset being at 0 and 1 and 1 and 0 produce the same outputs. But now when set and reset are both at 1, we get no change at the output. So that's the only difference in the construction that uses NAND gates as opposed to the construction that uses NOR gates. Let's look at something now called an SR latch with enable, which is a more useful version of a traditional SR latch. We have the SR latch as we have seen it before here, with inputs R sub 1 and S sub 1. Now we also have added this whole front end system here with the real inputs S for set and R for reset, and then an enable input. Now R1 is the output of a NAND gate with inputs S and enable, so it has the function S enable parentheses prime. S sub 1 is the output of a NAND gate with inputs R and enable, so it has the function R enable prime. Let's say that enable first is 0. That means that R sub 1 is equal to S times 0 prime, which is 0 prime, which is 1. This means also that S sub 1 is R times 0 prime, which is 1. If both of the inputs to a traditional SR latch with NAND gates are 1, that means that you get no change at the output. So when enable is a 0, we never get any change at the output. Now let's look at what happens when enable is a 1. If enable is a 1, that means that R sub 1 is equal to S times 1 prime, so that's S prime, and S sub 1 is equal to R times 1 prime, which is R prime. I'm not going to go through the whole truth table because we would have to identify all values of S and R and then get S prime and R prime as the inputs to the traditional SR latch. But the truth table ends up looking like this. Again, when enable is a 0, we never get any change at the output for any value of S and R. When enable is a 1, we get all of the traditional SR latch functionality. Again, we have an unstable state. In practical use, we want to try and avoid that state. But when S and R are both zeros, we get no change at the output. When S is a 0 and R is a 1, again that refers to this S and this R, we get Q is equal to 0 and Q prime is equal to 1. When S is equal to 1 and R is equal to 0, we get Q is equal to 1 and Q prime is equal to 0.